Okay, so you know what are molecules, right? Water, CH4. I'm going to mainly speak with you, so please respond. Water, CH4. Then there are a lot of, what's it called? CH2, CH3, whatever. These are molecules, right? Now, how are the shapes of these molecules are determined? They're basically determined by the arrangement of valence electrons in the central atom. Look, each and every molecule here has a central atom. In the case of, let's say, if in the case of ammonia, ammonia is also a molecule. In the case of ammonia, the central atom is nitrogen. And the arrangement of electrons basically determines the shape of that particular molecule. So, say for instance, there are two types of, electrons. You have lone pair of electrons. You have lone pair of electrons right here, and then you have the bonded pair of electrons, which basically produces the bond between the two types of atom, between the central atom and the side atom basically. And in this case, the bond which is being produced is obviously covalent bond, because covalent bond is the only type of bond which is produced through sharing of electrons, not by gain or loss of electrons, because we all know that the gain of loss of electrons results to the production of ionic bonds, isn't it? Right. I Here you can see it's given the lone pair of electrons are valence electrons that are not shared with another atom, and bonding pair of electrons are the valence electrons that are involved in the covalent bonds. So I guess you can understand what are these are the lone pair which are not involved, while the bonding pairs are basically involved. So this is one example basically you can say of how molecular shape is done. Now there is a theory which basically supports it. It's known as the electron pair repulsion theory. The shape of a molecule, if we, like basically what? Previously, we basically told that the shape of molecules determine the arrangement of valence electrons. Now we'll go a little bit of advanced, which is we are going to, emphasize on that statement by using a theory known as the electron pair repulsion theory. So the shape of the molecule is determined by the repulsion between the pair of electrons around the central atom. So as you can clearly see, all the electrons are negatively charged, and we know that like charges repel. So the bonded electrons which are present down here, they basically face repulsion. And due to this repulsion, and also not only the bonded electrons also face repulsion from the lone pair of electrons as well, because at the end of the day all of them are electrons, right? And all of them are negative charges, so eventually they will face repulsion. It's just that the degree at which they face repulsion is different. You can clearly see that the repulsion faced by what, like the degree of repulsion among the valence electrons around the central atom is not the same. Look, it's written here, the maximum degree of repulsion is between the lone pair of electrons with each other. So they are trying to say that if there is another lone pair and another lone pair, then the repulsion between the lone pair electrons will be the highest. Then the second highest repulsion will be faced between lone pairs and bonding pair of electrons, which is this one. You see the blue sign, blue arrow sign, that one. And the bonding pairs will have the lowest degree of repulsion. What they're trying to say is that the bonding electrons will receive the lowest repulsion. So we can just easily write LP BP is greater than BP. Am I clear? This is the priority. The repulsion faced by the lone pair electron is highest, then lone pair bond pair is lowest, and obviously then and so on and so forth. BP. So these are basically whatever I explained, provided in professional words. You can take the notes. Okay, the electron pairs arrange themselves around the, why it is called electron pair repulsion theory. It's because the electron pairs arrange themselves around the central atom to minimize their repulsion. Now based on this criteria which I've written, based on this criteria, if they arrange themselves around the central atom, they will face minimum repulsion, and this will result to the shape of that particular molecule basically. Now obviously the the number of lone pairs and the number of bond pairs are different in, it's not same in every molecule, right? So depending on the number of lone pairs and the number of bond pairs, the shape is determined. Say for instance, in water we have two lone pairs, isn't it? But in the case of what in the case of ammonia, we just have one lone pair, right? So obviously its shape will be different, isn't it? Did you get it? Because the repulsion faced by two lone pairs is greater than the repulsion faced by one lone pair. Am I clear? Okay, so that's how he it basically goes. Moving on now, what's it called? There is a thing called bond angle. Bond angle is the angle that is formed between two adjacent bonds around the central atom. The bond angle is reduced by different repulsions exerted by the lone pairs and bonding pairs. This bond angle is basically the main fact. It is the main reason, or it's how basically the shape of each molecule is determined. The bond angle for each molecule is different, and I told you why the bond angle is different, because the repulsion is different in each and every molecule. Am I clear? Due to this, so what is this angle? It's the angle formed between two adjacent bonds around the central atom, and the bond angle basically is reduced, in other words you can say varies, by the different repulsion exerted by the lone pair and bonding pairs. So say for instance the bond angle for water will be different compared to that of the bond angle in ammonia. A little while later you will see the drawing, and then you will understand. So the expected bond angle in the ammonia diagram is above is 120 degrees. So they're trying to say that depending on the considering there is only one lone pair and there are three bond pairs, and the repulsion that they faced according to this criteria, the bond angle will be 120 degree. However, the lone pair adds an extra area of repulsion. This reduces the bond angle to 170 degrees. They are trying to say that if the lone pair was not present, then it would have been 120 degrees. But lone pair basically adds an extra area of repulsion, which kind of reduces this bond angle to 107 degree. Am I clear? So eventually, the ammonia bond angle is 107 degree. Do you understand how how it goes? When you draw the 3D molecule, then what did they say here? Between two adjacent bonds around the central atom, this angle is basically 120 degrees. Sorry, not 120, 107 degrees. Am I clear? Hello? But in the case of water, let's say, what do we have? 104.5 degree, considering there are two lone pairs of electrons. Am I clear? You will see a chart a little while later. Okay, this, and why is it important that the bond angle reduces? This ensures that the maximum separation and the minimum repulsion between these pairs of electrons, which again basically supports our electron pair repulsion theory. Am I clear? So the reduction in bond angle is basically to ensure maximum separation and minimum repulsion between the pair of electrons, and this will basically so that the electron pair repulsion is supported. Am I clear? And it's the basis of which the shape of that particular molecule is determined. Now, how can you draw the molecules? Well, it kind of depends on a lot of ways. Like these are some of the steps. Yeah, say. Minimum repulsion. What do you mean by that? Minimum repulsion. Yes, it will face more repulsion. Like if it separates, like if the distance increases, I mean, what they're trying to say is that if the distance increases, if you said that lone pair kimba lone pair bone pair, you know gets more repulsion, isn't it? So if the distance increases, maximum separation will take place, isn't it? So that's what they're trying to say. So if the distance increases, the maximum separation takes place, and if the distance also increases, at one point of time they will face minimum repulsion. Do you understand what I'm trying to say? And if minimum repulsion bolte, for instance, if they like look, let's say you give a lone pair, okay, and then you give another lone pair, what will happen? They will face the greatest repulsion, isn't it? At prothome, and then due to the facing the repulsion, due to facing the greatest repulsion, they will separate from each other until at one point of time the repulsion becomes minimum and they get maximally separated. Did you understand now? Hmm. So this process leads to the production of the shape of that molecule, basically nothing else. Okay, now this is where I was trying to say. This you can clearly see, this is the table that is very very important for each and every you can see that for if there are two bonded pairs of electrons around the central atom and zero lone pairs, then the angle will be 180 degree, and obviously the molecular shape will be linear, and this is the diagram you can clearly see. For carbon dioxide, if there are two bonding pairs around the central atom, zero lone pairs, So 180-degree, linear. Look, there is a pattern. Do you see the pattern? Do you see the pattern? I think you can see the pattern, right? It's kind of simple that if you have two bonding pairs of electrons around the central atom with zero lone pairs, you are bound to have 180 degrees as the bond angle and the molecular shape will be linear. This is the diagram basically. And but in case of water, check out. It also has two more lone pairs as well. So what will happen? This will result to the reduction of bond angle from 180 to 104.5 degree and it will result to the diagram of a V shape. And this is the diagram you can see. Do you see it? Little while ago I showed you. Again, look, zero lone pairs. Again, the bond angle increased to 120 degrees with three bond pairs. It's a trigonal planar. This is it. So there you go. This is a diagram. Oh, by the way, BCl3. Uh, these are just examples of the molecules. These are just examples. It's not like that there can be. It's not like that BeF2 is the only linear molecule. There could be others as well. Say for instance, magnesium F2. It could be that as well, right? In that case, magnesium will be the central atom. Am I clear what I'm trying to say? Okay, so that's how it basically goes. You can clearly see that. So it basically, yeah, so it basically depends on the amount number of bond pairs and electron pairs. That is why it's recommended that you remember this table. Then you can basically interpret any sort of diagram and angle. Am I clear? For it's pretty simple, isn't it? Four bonding pair 109.5 with zero lone pair. Three bonding pair, zero lone pair 120. Like this you will memorize. Am I clear? It's pretty simple. And this is the tetrahedral shape. You can see that 109.5 degree. Again they give you three examples. You can see C2H6 diamond NH4 plus tetrahedral. You can see that. But check this out. Three lone pairs and one bond pair again results to the reduction of a bond angle to 107 degree, and this time it is not tetrahedral, rather it's trigonal pyramidal. Did you see that? Did you see the reduction bond angle due to the lone pair of due to the existence of a lone pair? Yes, exactly. Again, these are some complicated ones, but you should also memorize octahedral when there are six bond pairs and zero lone pairs, and five bond pairs and zero lone pairs. In that case, the bond angle varies. It's not actually like there are two bond angles in this case. One you can see 90-degree, and another one here is 120-degree. In the case of what six lone pairs is six bond pairs as well. The what's it called? There are two bond angles. One here 90-degree and the other here 180-degree. In both cases the shapes are also different. You can see this is trigonal bipyramidal, this is octahedral. Did you see that? You can see that basically. So it all sorry. Yes, from both sides. It is very important that 107 is present in both sides. Only in the case of trigonal, bipyramidal, and octahedral, there are two bond angles. Like for instance, here you can clearly see that in some bonds have, I mean, between two bonds, in some bonds they have 90-degree between them, and in some bonds there is 120. Only in the case of trigonal, bipyramidal, and octahedral you get to see two bond angles. But all others, it is because of the it's the nature of it. They have checked in the chemistry. Nothing to do, they found it. এটা কেন গেলে এখন একটু ডিপ রিসার্চে চলে যাবে, which is out of your syllabus. Am I clear? So just remember this for trigonal, bipyramidal, and octahedral. In the case of five lone pairs and six lone pairs, it's just unique for five lone pairs and six lone pairs, nothing else. Okay, and others are kind of you can see. So my recommendation will be to memorize the you know pairs of the combination. Am I clear? Just remember the combination and the bond angle. Then you can interpret any diagram and any EA. And this is like to draw 2D molecules. This was what? This was a 3D, right? This was 3D. Now it's the same thing. If you want to draw 2D, that's how you can draw. At first, obviously, you find the central atom of the molecule. The central atom is the one that forms the bonds, obviously. Then use the given formula to determine the atoms around the center. Say, for instance, H2O. In this case, who is the central atom? Who is the central atom? Oxygen or hydrogen? Obviously, oxygen is the central atom, isn't it? This is the first step. Then you use the given formula to determine the atoms around the center. You do that using this formula. Then you link up the atoms with single bonds. I think you know that, right? How to do? It's pretty simple. O, this one. Am I clear? So I think you know the 5 steps what they're trying to say. So, and this is like, they've just given you or just a little bit more clarity, that hydrogen has one valence electron, beryllium is two, boron has three, and that's how basically it goes, basically. And remember one thing, what is octet? When out these are all outer shells, I think you know that, you have learned it in IGCSE as well. So the when the outer shell becomes full, then that is known as octet. Am I clear? When the outer shell is full, that scenario or that state is known as octet. Now there is another problem. Some electron shells have more than 8 electrons, so in that case that is known as octet expansion. Am I clear? Like for instance, oxygen right here, what oxygen has how many outer shell electrons? I think we know this, right? 2 6. So already one electron it's sharing with hydrogen, another electron is sharing with hydrogen, right? So 2 electrons gone here, isn't it? That means here 1 2 3 4, 1 2 3 4 5 6 will, along with hydrogen, provides one more electron, and this hydrogen also provides. So total what? This is octet, isn't it? Considering it has 8 electrons, right? But in case of sulfur and phosphorus, there are more 2 electrons. For instance, more 2 electrons. Let's say this is sulfur. Sulfur is more electrons basically. So this uh, it can happen. I will I can show you if you want, but I will show you later basically. If there are two more electrons, just remember that if there are two more electrons than 8, then it's known as octet expansion. Am I clear? That's it basically, nothing else. It is very few elements, you can clearly see few elements like sulfur, phosphorus and bromine. Just remember these three. In the when the central atom is sulfur, phosphorus and bromine, only in that case you will see the production of octet expansion and nothing else. Okay, that's it. And how do you show the double and triple bonds? For example, you can show the double bonds, right, by showing what, like this, right? Two bonding pairs represent what? Double bond, isn't it? And in the case of triple bond, how do you show? For instance, this one, how do you show? Three bond pairs, like this. That's what they're trying to say. Okay, I think you know this. That's it. Moving on, now you have understood the bonding pairs, lone pairs. Now we need to understand what are these bonds, please. What like covalent bonds? There are two types of covalent bonds you need to understand. The first one is a pi bond and the another one is the sigma bond. Now let's talk about the sigma bond first. What is sigma bond? Covalent bonds involving the sharing of electrons between non-metals, those are known as sigma bond. And how do these sigma bonds get produced? See, each atom must have an orbital s or p with an unpaired electron. I think you have read this in the previous chapter, right? Okay, I'll explain that, no problem. But overall, I think you are familiar with the s orbital. It is spherical, isn't it? You have seen that. So what happens is that these two s orbitals are what? Regions of electrons. All right, that's what it is basically, the regions of electrons, basically nothing else. So these s when s orbitals overlap like this, you can clearly see when the s orbitals overlap করে যে এই শেপটা তৈরি হয়, then the bond which is produced is known as what? Sigma bond. Am I clear? This is a covalent bond, but this has a very nice name called sigma bond. Okay, the combined orbital is formed from the overlapping of the two orbitals from the two atoms. The combined orbital contains two electrons from the different atoms, isn't it? Like one electron is being donated from here and another electron is being donated from there, right? This results to the production of that, we write in the diagram, isn't it? That bond is this bond is basically what? Sigma bond. Am I clear? You understand? Yeah. This is from two different elements. Like for instance, the s orbital of for instance, the you can clearly see the s orbital. Where is it? Water. In the case of water, let's say the s orbital of what? Hydrogen, and the what? S orbital of oxygen. Did you understand? Now there are other ways also sigma bonds can be produced. Say for instance, the p orbital, You know the p orbital is dumbbell shape, isn't it? It's given in the book. P orbitals are dumbbell shape. So when a dumbbell shape p orbital overlaps with s orbital, this can also result in the production of a sigma bond. So actually there are three combinations when sigma bonds can be produced: the overlapping of two s orbitals, the overlapping of one p orbital and one s orbital, the overlapping of two p orbitals. Am I clear? Overall, in three of the cases, the bond produced is sigma bond. You can check out here basically. Now remember one thing: sigma bonds are very strong because the electron density is concentrated between the two nuclei. So what they're trying to say is that, say for instance, the electrons which are being donated, the all the electrons are basically concentrated in one region basically. This basically creates the force of, as a result, the force of attraction or the force of electrostatic attraction between the nuclei. Like this is a nuclei, I think you know that, right? Like s orbital is what basically, it's like, this is the nuclei of one element A, and that's the nuclei of element, let's say, B. All right, so element A and element B, or it could be both element, like the element could be of the same type. If let me use an example and then I can show you. Hydrogen, this is a diatomic molecule, right? Isn't it? So what is this bond down here? This is a covalent bond, and this is an example of a sigma bond. Basically they're trying to say is that, obviously, s orbital, right? So what they're trying to say is that the s orbital of one hydrogen atom donates an electron, while the s atom of another hydrogen donates an electron, and this results to the production of the sigma bond. And since all the electrons are concentrated in one position, the force of attraction between the two nuclei of these two atoms is very strong. And as a result, due to this force of attraction being strong, the sigma bond is overall stronger. Am I clear? Why is it strong? Did you understand? Hmm? Yes, yes, exactly. So that's how it goes basically. Alright, I think you understood what are sigma bonds. Let's move on to what are pi bonds. A double bond is made up of a sigma bond and a pi bond. So basically, a pi bond is only present in a double bond. So a double bond is made of what? A sigma bond. So that also means that without sigma bond, pi bond cannot be also present. But how pi bond is produced? This is very important. Pi bonds have two areas, above and below the axis, joining the two nuclei, and it is only produced by p orbital overlapping. But do you see the orientation in which the p orbitals overlap? In the case of here, the p orbitals overlap side, what's it called, they overlap what, like, they have what, like, horizontally they overlap, isn't it? But in the case of pi bond, vertically, or what, sideways they overlap. Did you understand? To pure only the overlapping of p orbitals, pi bond is produced. Okay, but overlapping in which way? Vertically overlap. Am I clear? Only by vertically p orbitals, if they overlap, pi bond can be what's it called, like, pi bond can be produced. You can clearly see. So what happens is that the electrons present above and below the axis, like axis is this one, this is the axis they're trying to say, this is the axis. So above and below the axis, the electrons here, এখান থেকে, they come and they're getting donated, and this results to the overlapping, and pi bond is produced. Okay, so if there are, like, say for instance, what example should I give? Okay, uh, carbon to carbon double bond. Okay, so this is a carbon atom and that's a carbon atom. So the p orbitals of these two carbon atoms overlap sideways, resulting, and how do they overlap? Like this. Am I clear? The electrons present above and below the axis, they overlap in these p orbitals sideways, and this results to the production of the bond called pi bond. This is also a covalent bond, but it's a pi bond. But always remember, there is one problem here. The problem here is that pi bond is weaker than sigma bond. Why? Do you know? Because pi bonds are weaker because of the limited overlapping of p orbitals, since they are sideways. Check out here. They kind of if they overlap in horizontally, if you check out the diagram, a lot of what, like, you can see a lot of overlapping happening, isn't it? A lot of area is covered during overlapping, and as a result, the force of attraction is also stronger. But here you can clearly see the area covered, or when they overlap sideways, the area covered is pretty less. So due to this limited overlapping of the p orbitals during sideways, the pi bond gets bigger. Did you understand what I'm trying to say? Okay, so this means that a double bond is stronger than single bonds, but it is not twice as strong. That means what they're trying to say, that a double bond is strong only because of the presence of a sigma bond. Am I clear? Am I clear? Can't you see here? A double bond is made up of sigma bond and a pi bond. Oh, the sigma bond basically comes here, overlapping of. Didn't you understand? Sideways overlap. Sorry, not so horizontal overlap. Did you understand? Like the p orbitals will overlap also sideways. They will overlap in both cases. Like say for instance, দেখা গেল so p orbitals কিছু p orbital এই দুইটা অ্যাটমের p orbitals গুলো সাইডওয়েজ কিংবা ভার্টিক্যালি ওভারল্যাপ করলো, আর এখানে মনে করো দুইটা p orbital কি হইলো horizontally, let's say they basically overlapped. So here a sigma bond and yes, yes, two times, so two bhabe. Didn't you see here how sigma bonds are produced by these three combinations? It could be an s and p orbital overlapping. Okay, it could be an s and p orbital overlapping as well. Am I clear? We don't know. It could be s and p orbital overlapping. It could be a p and p orbital overlapping. It could be what, s and s orbital overlapping. Am I clear? Sigma bond will be produced in a double bond. One of the bond will be sigma bond, and it doesn't matter by which combination it gets produced. But main thing is that it's constant, that the pi bond which is produced, it has to be p orbitals, and the p orbitals have to overlap sideways, not horizontally. Am I clear? Okay, so these are the similarities and differences. You can check it out. That the differences is pretty simple. What are the similarities? Both involve the overlapping of two atomic orbitals, obviously. Both involve in electrostatic attraction within the bonding and positive nuclei. I think you know that. And the differences are, you can check it out. They are present in non-covalent bonds, but they are present in double bonds, obviously. And obviously, they are produced by end-on overlap, like horizontal overlapping, and sideways vertical overlapping, obviously, pi bond. And only one lobe from each orbital is overlapping, and here two lobes from each orbital overlapping. What I'm trying to say here, do you see the lobes here? This is one lobe and that's another lobe. Am I clear? But here you can see only one lobe, like only one lobe is being produced. That's what they're trying to say. And obviously the end on overlapping sigma is stronger, the sideways overlapping makes it limited, so pi bond weaker. Pi is more difficult to break than sigma, obviously because of the first previous reason, and pi bond is kind of breaks easily because of the previous reason. And sigma bond allows rotation around the carbon to carbon single bond, but yeah, so they told you sigma bond is kind of difficult to break than pi. What's the issue? And then there is sigma allows rotation about the carbon to carbon single bond, and pi does not allow rotation on the carbon to carbon double bond. Okay, what they're trying to say here about this rotation thing is pretty simple. Say for instance, carbon to carbon single bond or carbon to carbon double bond. So we have what here? We have a sigma bond when you have a pi bond here, right? So let's say for instance Cl is connected, and let's say here for instance Br is connected. Now due to the presence of pi bond, rotation is not possible. That means they're trying to say that Cl cannot, like, we cannot like Cl cannot like the whole molecule cannot break, rotate. That means this molecule cannot become like this. Am I clear what I'm trying to say? Like ACL and Br won't go up and H won't go down. There is a restriction in the rotation of this bond due to the presence of pi bond. Am I clear what I'm trying to say? Like the orientation of the molecule won't change. Look here, the orientation changed, isn't it? The what happened here is pretty simple. The chlorine went up, like this went up, and this came down, like but through rotation. This went up, this went down due to rotation, but this rotation is not possible. Yes, exactly. Remember that. Why কেন হবে না? It's used. I don't want to go deep, but just remember that the pi bonds do not allow that. That's it. Yes. Let's move on to ionization energy. Look, ionization energy is the energy change that is associated by the removal of an electron from an atom. Okay. The first ionization energy is the energy required to remove one electron from each atom. Okay, I think this is the definition. Remember it. Electron remove করার যে energy লাগে ওটাকে basically we call ionization energy. And what is first ionization energy? The energy required to remove one electron from each atom. Please remember this definition. 3 star. They provide you define first ionization energy. Okay, remember this. So what they're trying to say is that the energy required to remove the first electron from the outer shell of an atom, that is basically the first ionization energy. So if the electron is removed, we all know positive ions are produced, so that's what is it. Singly charged positive ions will be produced. Why singly charged? Do you know that? Because one electron is removed. And the condition here is that both the atoms and the ions produced must be in their gaseous state. Am I clear? And ionization energy is endothermic because energy is absorbed to overcome the attraction between the nucleus and the electrons. I think you know that. Obviously, what is endothermic you learned in unit 2. So I guess I don't have to explain that one. That means ionization energy is what? Will it be positive or negative? Exactly. Now, what are the factors that affect the ionization energy? There are three main factors which would increase the ionization energy. Well, you have the nuclear charge, you have the radius, you have the electron shielding. Look, the greater the proton number, the more the attraction between the nucleus and the electrons will happen. Okay? So, if the greater the proton number, more attraction between the nucleus and electrons happen. So, what will happen? More energy, will there be an increase in the ionization energy? Obviously, right? Because you will be requiring more heat energy to remove that electron, considering the attraction is high. Radius, smaller the radius of the atom, the shorter the distance between the nucleus and the electrons, isn't it? Did you understand what I'm trying to say? Did, did, yeah, why? Because of the what? Because of the first reason. If the distance decreases between the nucleus and the outer shell electrons, won't there be more attraction? So if there is more attraction, won't the increase in ionization energy will take place? I think you understood. And the third factor is electron shielding, the blocking of the nuclear attraction on the valence electrons due to the presence of inner shell electrons. See, compared to helium, hydrogen, and lithium, in lithium you see there are two shells, right? So the outer electron right here, doesn't it face repulsion from these two inner electrons compared to hydrogen and helium where you don't have any inner shell? Do we have any inner shell here? We don't have any inner shell, isn't it? So the repulsion being faced by this outer electron from these inner electrons, that repulsion is known as electron shielding. Am I clear? Okay. So if there are fewer inner shells, the higher ionization energy will take place. Okay. Always remember this. So helium has higher ionization energy than hydrogen due to its higher nuclear charge. Did you understand why helium has higher ionization energy than hydrogen? Because it has a higher nuclear charge. Why does it have a higher nuclear charge? Can you tell me? Exactly. Both in helium. How will the radius increase? How? What are you trying to say? How will the radius increase if the proton number increases? Radius depends on the number of electrons, isn't it? Say for instance hydrogen, there is one electron. We know the first shell can accommodate up to what? Two electrons, isn't it? So the radius is same. There is no. Is there any extra shell here? There is no extra shell. So how come the radius is increasing? Here the radius factor is not into taken consideration. Then electron shielding is not into taken into consideration because there are no inner shells inside. This is the only shell present, right? The only taking factor that is taken into consideration here is nuclear charge, because the nuclear charge is not same. Did you understand? That's what I'm trying to say. But check out in lithium. Do you see in lithium? In lithium, what is it? What is the what's it called? What is the proton? Yeah, three protons, right? You have three protons, and you also have two shells. There is that means there is one inner shell, isn't it? So that means what? Here the radius increased, and at the same time the proton number also increased, and at the same time there is some electron shielding taking place. So you have to think deeply. Not every case the factors are not in these two cases the factors are two factors are not changing, only one factor is changing, but in this case three factors are changing. Look, helium and hydrogen have higher ionization energy than lithium because of their smaller radius and less electron shielding. Makes sense. Don't they have less lower radius than lithium? They do have, right? And don't they don't have inertia, so obviously their electron shielding will also be less. Like the electrons, the outer electrons obviously will won't face any shielding because there are no inner electrons. Did you understand why lithium will have lower ionization energy? Did you understand? Exactly. Yes, yes, the nuclear chargeটাকে basically compensate করতেছে. The nuclear charge is not the nuclear charge factor is not taken into consideration, rather than the radius and the electron shielding is taken into consideration, because electron shielding and radius basically plays a better role here, or a greater role here in the case of decreasing the ionization energy. Did you understand? Now let's move on to successive ionization energy. The sequence of ionization energy to remove electrons is until only the nucleus is left. That's basically successive ionization energy. So that's what it is: first, second, third. What do you think? Don't you think the second ionization energy will be greater than first? Don't you think এটা বেশি হবে না? থার্ড উইল বি গ্রেটার দেন সেকেন্ড, বেশি হবে না কি হবে না? অবশ্যই হবে। Obviously the second will be greater than first, the third will be greater than second. The energy to remove electrons increases steadily as the charge on the resulting ion gets greater. Check this out: A plus, and then you're what, A plus take A2 plus, A2 plus take you want to remove another electron. So obviously the what charge is nuclear charge is increasing. So not, sorry, not nuclear charge, like the ionic charge is increasing, isn't it? So obviously more energy will be required. So these are the three factors do also contribute to the steady rise in successive energy. Remember that the three factors which I have discussed below, these also contribute to the increase in ionization energy as well. So you should also remember these are the format of writing the ionization energy equation. So please memorize this as well. Let's move on. This table or this note is very important. You should remember this. Look, this is a graph showing the successive ionization energies of the sodium atom. I'm just giving you an example basically for understanding. The successive ionization energies show big differences. A logarithmic scale is used to fit them all on the y-axis. So in the y-axis, logarithm of all the ionization energies are taken and then drawn, and the number of electrons in the x-axis is provided. And to be honest, this graph related question will come in your question paper. See, the first electron removed, that is the first ionization energy. The second electron which is removed. Now do you notice here that we see a big jump? Don't you see a big jump? What does this big jump represent? Look, this is the electron which is being removed from the outer shell of sodium. After that, the second electron is being removed from where? It is being removed from the what? Inner shell, isn't it? Right? So when there is a shell change, there is a big jump in the ionization energy. Okay, now since the rest of the electrons 1 2 3 4 5 6 7 8, since 1 2 3 4 5 6 7 8, since the rest 8 electrons are removed from the same shell, there will be a steady increase. There won't be a big jump because all of them will possess the same energy. But again, after the 8 electrons are removed, again, what is it, 1 2 3 4 5 6 7 8 9, after the ninth electron is removed, when you want to remove the 10th electron, which is this one, and the 11th electron, which is this one, you will again see a greater big jump because the shell is again changing. And then you see right here, did you understand the whole thing, why the energy change is happening? Yes, electron, you are removing the electron, but did you understand why the energy required to remove each and every electron is increasing? Did you understand why? Because the shell is changing. Did you understand? So this proves what? All the electrons which are removed from the same shell, they all have the same energy. So as a result, they will have what, like comparatively similar successive ionization energy basically. But the ones if you whenever there will be a change in the ionization energy, what will happen is going to be pretty simple. You will see a big jump in you will basically see a big jump in the ionization energy, and there you go. That's how it basically works. So like this, all the 11 electrons can be removed, and that's how you can show the whole diagram. So you can check out whatever I have explained. They're provided in the professional words. The first electron has the lowest energy because it is farthest from the nucleus. Obviously it will experience the lowest force of attraction. The first electron is also shielded by the inner electrons, and you can understand that, which blocks the nuclear charge. The shielding and the radius decreases as more electrons are removed, and that increases the ionization energy. This is very important. After the look, remember one thing: the first electrons is shielded by the inner electrons, which blocks the nuclear charge. So what happens is that after the first electron is removed, the shielding and the radius decreases, because as more electrons are removed, what happens as more electrons are removed, what is happening? The uh, the radius between the remaining electrons decreases, because if as more electrons are removed, the force of attraction between the nucleus and the remaining electrons increases, and that is why the radius decreases. However, there is a sharp increase in the value of ionization energy between the first and second electrons. You can clearly see that there is a sharp increase between the first and second electron. Why? I think you understood. Because the second electron is in a quantum shell closer to the nucleus than the first electron. So obviously the electron which is much more closer to the nucleus, that will have a higher force of attraction compared to the first one. So it also shows that sodium has only one valence electron. Valence electron basically means, what do we know about it? 281. So that is the valence electron sodium has. And there is a gradual change in the ionization from the second to ninth electron, because like I explained a little while ago, these 8 electrons are basically present in the same quantum shell. So as a result, they will possess the same ionization, same energy. So as a result, they will comparatively will take similar ionization energy to, or energy to be removed from their quantum shell. The big jump from the ninth and 10 electrons, you can see from ninth to 10th we see a big jump, because the 10th electron is in a shell closer to the nucleus. You can see 10th and 11th, a little while ago I explained. And obviously this proves that 10th and 11th will have the highest energy, considering that the most closest to the nucleus, and the last two electrons are not shielded by other electrons, and that is the another reason you can say, explains why they have the highest energy. Okay, so with this, let's move on to the last one, about regarding ionization energy, and that is some data booklet values they've provided. Like now, instead of providing the graph, they might just provide you the value of the ionization energy. So you have first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 13th. So you can also predict the identity of the element by using the successive ionization energy data. Look here, the number of jumps in the successive ionization energy shows the number of shells and the period number. This is very important. The second thing that is also important is that the number of electrons before the first jump indicates the number of valence electrons and the group number. This is important. Now let's say for instance this one, right here, for instance, you can see clearly the big jumps in the ionization energies are shown in the table as orange lines. So you can see clearly that there is a big a big jump from 570 to 1800. So this basically indicates this is the electron which is removed. It was removed from the first shell, and then the second electron which was removed, it was basically removed. We see a big jump, so that means this is the second electron is removed from another shell. And then the third electron, we see not that of a big jump, so that would be these two electrons will be present in the same shell. So again, after at the fourth electron you see a big jump, so these two electrons will be present in another shell. So that's two shells for you. Again, fourth, fifth, sixth, if we get to see that three of these electrons, there isn't a significant big jump. You get to see there isn't actually a significant big jump. You get to see like they're going and happening like this until the 11th electron. Until the 11th electron, you get to see that we get to see a very big jump again. and then you get to see a very big jump. So this kind of indicates, what does this indicate? This basically indicates that the first three electrons were present in the first outer shell, and the fourth electron to 11th electron we did not see any big jump. Similarity, there was a similar pattern in which the ionization energy increased, while removing the 12th electron we saw a big jump. So basically, in other words, we can understand that these electrons were present in the second shell, and the last two ones were present in the third shell. And overall we can say that there are three shells in this element. Okay, so that's how things work. We can basically, so by identifying the number of jumps in the ionization energy, we can understand the number of shells. And we know that the number of shells in an element represents the period number in which it is present. So there are three shells, it's in period third period. Now, also another thing is the number of electrons before the first jump indicates the number of valence electrons and the group number. So obviously the what's it called, the first shell is basically the outer shell, the outermost shell, to be honest. And since there are three electrons in the outermost shell, and we know that the electrons, the number of outermost electrons represents the group number. Since there are three outermost electrons, this indicates that this particular element is in group 3. So like this we can identify whether, in by analyzing the ionization energies, we can basically confirm the period number and the group number in which this element is present. Okay, so with this our class is over. That's it for today. Bye bye. The next part is to understand what is molecular polarity. Okay, so in this case we are basically to discuss what is electronegativity. It's basically the tendency of an atom to attract the shared electrons in a covalent bond. So obviously if the electronegative value is greater, uh, the atom will basically gain the ability to attract more shared electrons. So in other words, if I say so, HNCl, obviously chlorine will have a higher the electronegativity of chlorine is higher than hydrogen. So as a result, due to its higher electronegativity or the tendency of it to attract shared electrons, so whenever the covalent bond is broken, only chlorine will have the greater power to take in the electrons towards itself. Now you should also remember that some of the trends, that is that electronegativity decreases when you move down in each group due to an increase in the electron shielding. And what they are trying to mean is that due to moving down due to an increase in electron shielding is that when you move down the group, there is an increase in electron shielding, considering the number of inner shells tend to increase. So if the number of inner shells tend to increase, the number of inner electrons also increases, and this results to the repulsion being faced by the outermost electrons, increased repulsion being faced by the outermost electrons from the inner electrons. Hence, electron shielding is there. So due to this, electronegativity basically decreases. Now across the period from left to right, there is an increase in the effective nuclear charge, which results to an increase in the electronegativity. What they're trying to say is that when we go from period wise from left to right, we see a trend in increase in the proton number, and henceforth this results to the increase in the nuclear charge of that particular element. So with the increase in the effective nuclear charge, electronegativity also increases across a period. And the element with the highest electronegativity, if we follow this trend, fluorine is basically the one which has the highest electronegativity with this element. And fluorine also has the highest effective nuclear charge, and it has the smallest radius and little electron shielding. Always remember that with the radius basically does not always remember one thing, that since the number of inner shells remains the same in a period wise, the radius won't increase that much. So that means the factor which is going to play a huge role in the increase of electronegativity is the nuclear charge, considering the proton number increases. On the other hand, when you go down the group, the nuclear charge, what's it called, the nuclear charge kind of changes, but the main thing is here the number of shells increases. So due to the increase in the number of shells, what is happening, the electron shielding is increasing because of the increase in inner electrons. That factor is going to play a better, huge role in order to cause a decrease in the electronegativity as we move down. So that's how it goes. Francium has a low now if you follow the group wise trend, then you'll see that in group 1 francium will have the lowest effective nuclear charge due to its larger radius and a lot of electron shielding basically. So if we say so, the nuclear charge tends to increase as we go down this way, and as we go down here, as we go down below, the nuclear charge plays a less role considering the distance between the outer shell and the nucleus increases. So the nuclear charge factor does not play a huge role in the group wise trend compared to the period wise trend. If we move on to the polar bonds, what are polar bonds? Non-polar and polar bonds are greatly determined by the electronegativity. So non-polar bonds occur when the electronegativity of the atoms involved in the bond is identical. Say for instance H and H, both of them have electronegativity of 1 and 1, and as a result the polarity which is being produced, what is polarity? Basically the production of the partial positive charge and partial negative charge in both of these atoms. This part, the production of these partial charges, this is basically known as polarity. Both of them have identical electronegativity. As a result, the bond which is produced, this is non-polar bond. All right, but in the case of HCl we know that chlorine has a higher electronegativity, and whenever there is a difference in electronegativity, that time we basically use an arrow in order to determine, to show the partial positive charge is produced. Obviously hydrogen will have positive charge and chlorine is going to be negative, and the arrow will be shown towards the chlorine considering it is more electronegative atom here compared to hydrogen. So why it is shown? Because due to this polarity, the more electronegative atom will have the power to pull the shared electrons in the bond closer to its side. So whatever say for instance there are two bonded electrons, so the tendency is that it will remain much more closer towards chlorine compared to hydrogen due to the higher due to the higher electronegativity of chlorine. So that is how it basically works. So in the case of polar bonds, the bonded electrons will stay more closer toward the more electronegative element, while in case of non-polar bonds the bonded electrons will stay in equal distances from both atoms basically. So that's how it works. If we move on, how can you classify bonds using electronegativity? So, well, there are some cases. For example, pure covalent bonds can only exist between identical elements such as hydrogen or oxygen. The electronegativity difference between identical atoms is kind of zero, and the electrons are shared evenly. In this case, this one H and H, if I say so, but here the electrons are not kind of shared due to the difference in electronegativity. So if you check out down here, how can you use the electronegativity difference to predict the type of bonding? This is very important. See, so if both of the molecules are identical, that means what? Let's say this is 1 and that is 1. So what is the electronegativity difference? 1 minus 1 is 0. So when the electronegativity difference is below 0.4, which is 0 obviously, that time we can say that the covalent character is higher in this particular molecule. But you can clearly see how the ionic character increases. Say for instance HCl, obviously Cl will have a higher what's it called, electronegativity. It's more electronegative than hydrogen, so obviously there will be an electronegativity difference. And if the electronegativity difference is between 0.4 and 1.7, after subtract and find it out, and if it falls between this range, then we can say it is having an increasing ionic character. So for example, in the case of two non-metals, for example chlorine and chlorine, we get to see zero electronegativity difference, so that is why it is a covalent compound. But in case of HCl, it is also a covalent compound, but it's just that what's it called, it's not fully ionic. It's not fully covalent basically. It is somewhat ionic as well. It also shows somewhat ionic character because the difference basically falls within this range. But in the case of one non-metal and one metal and one non-metal, this is fully ionic bond considering the electronegativity difference of Na and Cl minus. If you find it out by checking out the electronegativity table in your book, if you just find it out, you will see you'll get a difference of 1.7 obviously when the when which falls outside this range. And whenever it falls outside this range, that means greater than 1.7, we can easily conclude the fact that these two basically produce an ionic compound. Okay, So in case of what are polar molecules, the next part basically. Now polar molecule is one which is basically uneven distribution of electrons. There are two types of polar. We have symmetric and asymmetric. Now symmetric is the one where all the atoms are all atoms at the central atom are identical. Say for instance CH4 and CO2. You can clearly see that this is a symmetrical molecule, considering the types of molecule, the type of atoms connected to the central atom is kind of same. But in the case of asymmetrical thing, you can clearly see one of the atom is different, so this makes this molecule asymmetrical. So whenever a molecule is symmetrical, that molecule becomes non-polar in straight words. And whenever a whenever basically a molecule becomes asymmetrical, and how can you identify asymmetrical? By checking the type of atoms being connected. So if one of them is different, then it becomes asymmetrical, and this kind of creates the polarity here. You can see the polarity right here, and that's how the molecule becomes polar. Many molecules contain more than one polar bond, yet the entire molecule is non-polar. Now there are some cases basically where you can find that even though one polar bond is present, the entire molecular yet remains non-polar. See for instance atoms that have lone pairs of, so there are several ways you can determine. Three ways are there. For example, atoms which consist of lone pair of electrons on the central atom are usually polar. Say for instance water and ammonia, we know that water is two lone pairs, then it is one lone pairs. Easily we can distinguish that both of them are polars. Okay. This also applies to all molecules with pyramidal or band shapes, considering they also have lone pairs. Symmetrical molecules have an equal distribution of electrons. They are always non-polar. As I said clearly, these are symmetrical molecules. They are always non-polar because they don't have any polarity present. Considering four of the considering four the pol you know the polarity of four of the bonds cancels out each other. Okay, what happens is pretty simple. The polarity which is produced in four of the bond, kind of all of them basically what's it called, cancel out each other. But this is only possible if all of them are of the same type. But if it's not of the same type, let's say for instance in this case it is hydrogen, one of them remains. Three cancel out, but one of the polarity do not cancel out. As a result, this whole molecule becomes polar. There's another way you can basically show polar molecules, and that is by using electron density maps. These are basically sketches of something something like this. So you can see in a non-polar bond, the electron density map is symmetrical, considering the electrons are shared evenly and there is equal distance between them. But in the case of polar molecules, the chlorine molecules are much more electronegative than hydrogen, and as a result, the electrons are much more attracted. The bonded electrons are much more attracted towards the chlorine nucleus, and as a result, get to see that the electron density map, the density of the map is much more greater in the chlorine side, basically. So, and that's how it works. We can also determine the polarity experimentally or practically by using a charged glass rod near a stream of liquid from a burette. Now if the obviously the water is a polar molecule, we know that, and it's kind of charged, right? We know that water contains partially positively charged and partially negatively charged air. So as a result the charged rod will basically able to attract the water, considering it's a polar molecule. But remember, non-polar molecules like hexane are unaffected because the non-polar molecules do not have any polarity present. They do not have any partial positive or negative charges, making them uncharged, and that is why uncharged molecules cannot be attracted by the stream of liquid. So that's how you can practically experiment regarding polarity. The next part is we need to talk about metallic bonding. Now, what is a metallic lattice? It's a regular arrangement of metal cations in a sea of delocalized electrons. The delocalized electrons are the valence electrons lost by metal atom. Now, delocalized electrons are those that are not associated with one particular metal atom. This is very important. You can clearly see that metal atoms, for example sodium or magnesium, whatever you name it, they basically lose their outermost electron, and this electron comes out, and the bond which is being produced, the force of attraction which is being produced after they get delocalized, in other words they get lost, the force of attraction which is being produced between the ion and this delocalized electron, that force of attraction is known as metallic bonding. Now, obviously, there are two factors which results to the increase of metallic bonding. That is a higher charge density of the cation, which is like Mg2 plus and compared to Na plus. Obviously, Mg2 plus is going to have a greater strength in terms of metallic bonding compared to Na plus, considering it is a higher charge intensity. It is a higher charge because first of all, there are two delocalized electrons per ion compared to one delocalized electron per ion in Na plus. So as a result, obviously the metallic bonding in Mg2 plus will be greater than Na plus. So this kind of aligns with our two statements provided right here. Metals like aluminum can produce stronger metallic lattice because of its smaller radius and higher charge. A large number of valence electrons, basically. Obviously, in the case of aluminum, we get 3 plus. Each ion is 3 plus. That means each atom basically loses 3 electrons. So 3 delocalized electrons get to produce the metallic bond. So obviously, the attraction between 3 delocalized electrons and an ion will be greater compared to the attraction between two delocalized electrons and one Mg2 plus ion. So that is how basically the strength differs, and that is the 2D structure of metallic bonding. Now if you want to compare between ionic and metallic bonding in terms of structure of the lattice, there are cations and anions involved, but in metallic the cations are dissolved or present in a sea of delocalized electrons. The electrostatic attraction takes place between cation and anion, but in the case it's between cations and delocalized electrons. Most people make mistakes, but I hope now by seeing this that you can understand and be aware later on. The strength of the bond. Now remember one thing, the strength here depends on the ion, the type of ions and the charge density present here. But in the case of metallic bonding, I think we have little while ago explained, it kind of depends on the type number of delocalized electrons and the charge density present in per ion. All right, now about the electrical conductivity is that ions can only move. Ions are the charged ones, charged species in the ionic compounds, and they can only move when the compounds are in molten or dissolved state. So that's kind of limits their conductivity. But in case of metallic bonding, they conduct electricity when solid or molten. They do not have any malleability property, but metals do have are malleable. In other words, malleable means they can be bent into shape. Malleable basically means bent ability ability to be bent to any shape. That's basically malleability. So because the cations can slide past each other, breaking the force of attraction in all directions. So the thing about metallic bonding is that they're found in layers. So the layers can basically slide. One can go this way, one can go that way. So since the layers can slide over each other due to the weak force of attraction between the metallic bonding layers, they have the ability to become malleable. That's how it works. Now there is one similarity between them, that is both of them are strong electrostatic forces of attraction. So obviously a huge amount of heat energy will be required to break both of them. As a result, wherever these two bonds are present in any, name it a metal or name it a compound, both of them will have higher melting point. So with this, I guess our AS organic chemistry's recap is complete. Tune into our exam essentials channel and subscribe to it for further updates. Thank you.